Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We have discussed a few physiochemical parameter such as pH, redox, such processes, and to better understand a few processes we are going to use isotope geochemistry. So, from today we are going to begin our lectures on isotope geochemistry. The very first few lectures will be on the introduction and making a base, because I understand many of you would not have undergone any geochemistry related courses. So, the few lectures that I will take, the first few lectures will be to introduce geochemistry, stable isotope geochemistry, radiogenic isotope geochemistry, the fundamentals of it, and then after that we are going to use some tracers particularly for some aquatic processes. Okay. So, each and every type of tool that we are going to use, I am going to introduce you to the fundamental aspects, and then we are going into the application part of it. So, let us begin isotope geochemistry lectures. We will start from this module. Now, to understand isotope geochemistry, why do isotopes form? Why does some isotopes are called stable isotopes, why some isotopes are called radioactive isotopes, okay, why radioactivity actually exists, okay, is dependent a lot on their nuclear stability, right. So, this nuclear stability, all these processes actually started since the Big Bang. Okay. Since the elemental process formations, from the time that the elements started forming. Okay. So, we are counting from that time. So, our first understanding should be that how these elements are getting formed. Okay. So, we are going to start everything from the starting point of our universe, that is the Big Bang theory. So, how do the elements form? That is the science of nucleosynthesis. Okay. If you want to go into details, you please look up into details, but I am just going to give you an overview of how certain elements are getting formed and why some of them are unstable, therefore, will go into radioactivity, certain very related to the scope of this course. Okay. So, very briefly about nucleosynthesis. Okay. At the very beginning means from the point at which time started, So, if I break down even seconds, sub seconds and all that. So, at 10 to the power minus 2 second, okay, when the temperature was 10 to the power 11 Kelvin, at that time there was just forms of protons and neutrons. So, just subatomic particles were there, and they were also constantly forming, okay. And we formed the first the electrons were getting formed, the neutrons were getting formed. So, they are in that stage. So, subatomic particles just started forming, okay. And the nucleus, okay. So, the nucleus, outside the nucleus, if a neutron is there, it is unstable. Okay. So, that will decay. So, neutrons getting decayed into proton plus an electron. Again, if a proton captures another electron, it starts to forming a neutron. Okay. So, such processes are going on. Okay. So, a neutron's decay period is 15 minutes. The half cycle of the half life of a neutron is only 15 minutes. Okay. So, imagine the time scale of those reactions. So, it is just happening extremely fast. From 10 to the power minus 2 seconds come down to 1 second. Okay. It is only 1 second past the Big Bang. And what do we have now? The temperature is around 10 to the power 10 Kelvin, and all the above reactions have shut down. So, all the subatomic reactions have shut down, and now we are left with only just imagine the number of protons and the number of neutrons that can be there Okay. So, we have 3 times as much as proton as compared to the neutrons. Okay. So, we are just left with a lot of neutrons and with a lot of protons. 3 minutes past Big Bang, that is 10 to the power 9 Kelvin at right now this temperature is, hydrogen starts forming. Okay. So, 1 proton and 1 neutron will form hydrogen and the mass is given. So, 2 is the atomic mass. So, hydrogen is getting formed and some energy is getting released due to that process. Okay. And these reactions, this chain of reactions is continuously happening. Okay. So, hydrogen again accepting 1 neutron. So, now it is tritium. So, 3 mass of hydrogen, that is again something. 2 hydrogen plus 1 hydrogen can now again is forming 3 helium. Okay. So, hydrogen and helium processes are going on, and what are we forming next? We are forming 7 beryllium and 7 lithium. So, from hydrogen we have helium, then we are forming beryllium and we are forming lithium. So, when the temperature of the universe started cooling below this 10 to the power 9 Kelvin, then these nuclear reactions were no longer possible. Okay. So, now we are left with a lot of hydrogen, a lot of helium and a lot of beryllium, lithium, and again a mass of protons and neutrons are also there. Okay. So, this is at 10 to the power 9 Kelvin a few minutes after the Big Bang. Okay. So, this is the process, okay, the initial first few reactions, okay, that happened about 13.8 billion years ago. Okay. G is billion years ago. Okay. That is responsible for the formation of hydrogen and helium, and then after, once the hydrogen and helium has formed, they started forming the main sequence stars. Okay. Where helium is inside the stars and hydrogen is mostly on the outside, and they started obviously they started ignition, they started now the forming of all other nucleosynthesis processes, and we at every stage we started to form different nuclei. Okay, we started to form different nuclei. So, during the stellar nucleosynthesis, that is during the formation of the stars, during the first when the stars started to burn, during that phase, okay, we started to form all the lighter nuclei. Okay, we started to form all the lighter nuclei. So, that means all the 1 to 10 atomic number of all the elements that is there, they started to form. Okay. And then again they started to fuse inside of the stars, and we can get up to iron. Okay, we got up to this element iron, okay, during this stellar nucleosynthesis processes. After iron, it started becoming difficult to form more elements. Then the stars started to move into explosive nucleosynthesis. That is another stage, okay, in the nucleosynthesis, and they started forming the heavier elements, the elements that are heavier than iron. Okay. Now, why we are stopping at iron, why we are stopping before and after things like that, why we are differentiating it between larger elements and lighter elements and all that, is because of the stability of the nucleus. Okay. Certain elements, okay, if we have to form, they have to undergo through more number of processes which are termed as N processes, S processes, R processes. Okay. If you are interested in looking deeper into how the individual elements are formed, I urge you to look into this very interesting topic of stellar nucleosynthesis and all the subsequent nucleosynthesis processes. I have referred William White book, the Geochemistry book, and in the isotope geochemistry book, the very first chapter, I think it will be on the stellar nucleosynthesis and the formation of elements, and you can see how the processes evolved during and after the Big Bang that led to the formation of these elements. Okay. So, just this is a very brief overview of how these elements are getting formed. Okay. That is during the first initial period of Big Bang, where we were mostly having a lot of hydrogen and helium. Then during stellar nucleosynthesis, we formed up to iron. After that, it moved to explosive nucleosynthesis processes, where we formed from iron all the heavy elements started forming. And during the galactic nucleosynthesis processes, some other elements, okay, such as lithium, beryllium, boron, they started getting forming. Now, all these processes, that means, are happening during the burning stages of a star. Okay, they are happening during the burning stages of star. So, if you want, you can go and look into it into more details, but from here we are just going to move into this direction of nuclear stability and why we see radioactivity and therefore use the isotopes to do some tracer activities in geochemical processes. So, again, just to show you the glimpse of what happens. So, the Big Bang, during the Big Bang, as I told you, we form the hydrogen, we form the helium, we have all the hydrogen isotopes are getting formed, some lithium and some boron also is formed during this process. Then we have the main sequence stars burning phases, that is the first phase is the hydrogen burning phase, we get 4 helium as a product. Then starts a helium burning phase, where we have all the carbon, helium, magnesium, oxygen and neon, which is that gas is getting formed. Then we form the carbon burning phase, where we have more elements are getting formed. Then the CNO cycle starts, it results into formation of more 4 helium, and there are a lot of spallation processes like the alpha process, E process, S process, R process, which can give to a variety of other transition metals, and it can reach up to 209. The R process can reach up to 254 mass number of elements. Okay. So, you see that in this other figure, where we have plotted the mass numbers versus the abundance relative to silicon. Okay. Why it is the abundance relative to silicon is being plotted? Because silicon is a very abundant element in the earth, alright. It is one of the most abundant element on the earth's surface. So, earth's mantle and its crust, silicon is the most abundant, one of the most abundant elements there. So, when we are comparing our silicon to other elements, okay. So, hydrogen, so this is talking about the entire universe, okay. So, hydrogen is many times more abundant as compared to silicon. Then we have, this is D, that is deuterium. So, helium is there, lithium is far less in number, beryllium is far less. So, these are different elements, group of elements whose formation was due to other processes, and they require such high temperature that they had not formed any further. So, during the different phases, that is the helium burning, carbon burning, oxygen burning phase, these are the subsequent elements that got formed till iron, okay, it formed, and after that you see the abundance of the elements is rapidly decreasing. Okay, the abundance of these elements is rapidly decreasing. Okay. So, as we go to more mass numbers, these are more controlled by the S and the R processes. Okay. So, when there are particular processes that relate to the that led to the formation of particular elements, for example, strontium getting formed, barium is getting formed, these processes are getting formed. Then we have these are more abundant therefore in the earth's crust, and not only on earth, maybe in the entire universe as well. So, xenon, which is a noble gas, neon, which is a noble gas, these are all there in the their abundance is quite high. Okay. But other than that, you see above this mass 56, the abundance slowly goes down. The abundance after mass 56 slowly starts to, it slowly falls down. We slowly have a very less abundance of these elements. So, let us look into this periodic table and see certain groups of metals. I think we have already done a bit, but we are going to, since we are going to talk about radioactivity, and we have to be cognizant of the metals that we are going to look and the pairs that we are going to look for. Okay. So, on this on this left side of the periodic table, we have the alkali and the alkaline metals. Okay. These elements, they tend to give up their electrons and they form cations. Okay. In the middle group, okay, in this middle group, they are the transition elements. They can give up an element, they can give up a electron, or they can accept a electron and change their valency state and oxidation state. So, this group of elements, they can behave quite variably. Again, this is a very particular group of elements which is absolutely here, starting from here. These group mostly accepts electrons, and therefore, they are called the anion group of elements. Now, let us see some of the few chemical properties. Okay. So, the energetically most stable and the most unreactive elements are of course the noble gases. Okay. So, we have helium, we have neon, we have argon, krypton, xenon and radon. Okay. So, these are the noble gases and they are there, they are stable, okay. They are very unreactive, they do not want to react anymore. So, they are mostly in the atmophile. Atoms, they, other than these elements, they form chemical bonds to attain chemical stability. Okay. So, they will be exchanging electrons, okay. Either they are giving out electrons, so they are cations, or they are accepting electrons, they are anions. The ones that give out the electrons, they are going to get positively charged, and mostly they will be called metals. Okay. The others which are gaining the electrons, they will become the negatively charged and they will be called the anions, and otherwise also known as the non-metals. Okay. And this mixture of metals and non-metals is what forms our chemical compounds, and they are going to form the minerals. Okay. So, minerals are metal and non-metal associations. Okay. For example, in silicates you will have some metal and you will have this SiO4 structure. Then there will be oxides. So, Fe2O3, one metal, one non-metal, or TiO2, one metal, one non-metal. Again sulphide, some kind of metal will be there, and then there will be an ion, that is in sulphides it will be sulfur, or in carbonates it will be this carbonate anion. Okay. So, this is how the minerals are formed, these are metal and non-metal associations. Okay. Now, even when forming these minerals, there are particular tendencies for the different elements. Okay. For example, certain elements, they are called lithophile elements. What do we mean by that? Lithophile, that means they have an affinity for silicate phases. Litho comes from the Greek, they have a Greek origin, and it is mainly implying for the lithosphere, which is part of the earth's mantle and the crust. Okay. And there mostly the silicate phases are the most stable phases. So, these elements and these oxides, they are concentrated mostly in this phase of the earth. So, that is the lithosphere, that is crust and the part of the mantle. Okay. And they will be mostly the calcium, magnesium, the lighter elements will be mostly concentrated in the lithosphere. Okay. Then certain elements, a group of elements, they are called the chalcophile. Okay. And they have the affinity for sulphides. Okay. They are more stable if they are in their sulphide formation. Okay. So, sulphide compounds and the transition metals, they are most likely to have this affinity for sulphides, and they are concentrated therefore in the core and depleted in the crust. Okay. So, more of iron, more of copper, more of all the sulphide loving elements, they will all get concentrated in the core, and we do not have their availability as high is in the silicate crust. Then another group of elements, that is the siderophile group of elements. They have the love for iron. Okay. They will love to be wherever iron is there. Okay. And again, since iron is itself a chalcophile element, siderophile elements also tend to form in the earth's core. Okay. They will remain in the earth's core, okay, rather than the oxygen rich earth's crust. Okay. So, the rare earth elements, the platinum group of elements and cobalt, nickel, these elements, they as well, okay, they like to be in the earth's core. And the last group of elements is the atmophile. These elements, as the name suggests, that they would love to be in the gas phase. Okay. So, hydrogen, carbon, nitrogen, oxygen, the noble gases, they will all love to be in the gas phase. Okay. So, if you see the breakdown of atmophile, lithophile, then chalcophile, siderophile, we will see here we have mostly the alkali and the alkaline earth metals. Okay. And here we have the strongest chalcophile elements. Okay. Here we have the strongest siderophile elements. Okay. So, this is the how we are now going to divide. Okay. We are going to divide into more details now. Okay. Let us see. So, in the first group of elements we are going to see is the volatile elements. Okay. So, our helium, neon, argon, krypton, xenon and hydrogen here, they are all the volatile elements. Okay. A little less semi volatile elements, then we have carbon, we have nitrogen, we have fluoride, we have chloride, we have sulfur and all these elements. Okay. They are slightly less volatile. Okay. Then which are the major elements? Okay. Some elements which are major in the earth's crust. Okay. So, we have sodium, we have magnesium, we have calcium, here we have aluminum, we have silicon and we have oxygen, and here we have iron. You should remember that iron had one of the highest abundances. So, it is also found quite abundantly. Okay. So, abundant, they are there in abundant in earth's crust and also in the mantle and in the core. Iron is found everywhere. Okay. But more in the earth's core. Okay. In earth's core and in the lower mantle, iron is more it is segregated more and it is there in higher concentration, and far as compared to crust, it is far depleted in the crust. Then we have the first transition metals, okay, first series of transition metal. So, this is the first series of transition metals that starts from scandium to zinc. Okay. Then we have certain noble metals. Okay. These are certain noble metals. Okay. That means they will be in very less amount, okay, and they will not be very reactive. They are very the noble term comes when they are very rare, their occurrence is extremely rare, and they will be mostly all be in the core, okay, and their occurrence is extremely rare. Then they are all very loving for iron, okay, they are very iron loving elements. Then we have a small group of elements which is called the high field strength elements, okay, another very different group of elements, the HFSE. So, here we have the zircon, we have the niobium, we have hafnium and we have tantalum. Okay, this is another very particular group of elements, and they are called because they have very high ionic charge. Okay, they are very high ionic charge, and they are very they form very strong bonds with the anions. Okay. So, they start forming a very high field, they have a very high field strength around their bonds. It is very difficult to break those bonds. So, that is why they are very stable minerals, they form very stable minerals. It is very difficult to weather them, and they are almost insoluble. Okay. They are very difficult to get dissolved in water. So, if you look into their concentration in water, you will find them in extremely low concentrations. Low means below, so PPT level concentrations, and probably to get them into some measurable detectable amount, you have to do a lot of pre concentration type of preparation techniques have to be used. Okay. So, they will be mostly occurring as very in dense minerals. Okay. They will be very heavy minerals, they will be in the dense minerals. Okay. Extremely non-reactive, they will not react with anything, they are difficult to weather and difficult to dissolve. Okay. So, these are very particular group of elements. Then what we have is the rare earth elements, and of course, we have the alkaline and the alkaline earth elements, that is lithium, beryllium, potassium, rubidium, strontium, cesium and barium. These are the alkali and the alkaline earth elements, and we have the rare earth and the related elements group. So, the lanthanum series, okay, and the actinium series. Okay. So, these elements, they again are called the rare earth elements, because again they are found in very trace their amount is very less in water, they are rare earth elements. Okay. Their concentration is very low, although they can be found commonly in particular group of minerals. Okay. And they are more in the core. Okay. They will be found more in the earth's core region, they will be more. Okay. Again they will form very dense elements, they will be very difficult again to weather. Okay. Now, let us see what is the stability, what is the structure of the nuclei, and thereafter we can understand why certain isotopes getting formed. Okay. So, the structure of the nucleus, what do we have inside a nucleus? Okay. Inside the nucleus we are going to find the protons, and we are going to find the neutrons. Okay. So, that protons and neutrons, they are called the nucleons. Okay. So, in an atom we have, so if I am looking at an atom, okay, we are going to have a nucleus, and we are going to have some electrons, right, that is, this is the electron cloud, and inside this nucleus we are going to find the protons and the neutrons. Okay. So, this is the electron clouds where the electrons are all constantly roaming around, and this is the nucleus where we are going to find the neutrons and the protons. Okay. So, if we take an example, now what is called the mass number? Mass number is the mass, actually the mass of the nucleus itself. Okay. So, the mass of the nucleus is the total number of protons and the total number of neutrons. Okay. So, we have n, which is the number of neutrons, and we have z, which is the number of protons. Okay. Now, mass number is n plus z. Okay. So, the total number of neutrons and the total number of protons. Now, protons, they define what is called the atomic number. So, they define something called the atomic number of the element, while the mass number is defined by the neutrons and the number of protons together. Okay. So, if the mass number of carbon is 12, then it has 6 electrons, it has 6 neutrons and it has 6 protons. Okay. So, sometimes it can happen that there is a mass different, okay, that an element will have different, will exist with different masses. And why will it be? That is due to the variable number of neutrons. Okay, it is going to be due to the variable number of neutrons. Therefore, the total number of nucleons will differ. Okay. The total number of nucleons, that is this number, will differ. Their atomic number remains the same, but their mass number is changing. Okay. So, for example, let us see uranium. Okay. Uranium has its atomic number 92 and its mass can be, one can be 235, one can be 238. Okay. And in both of that you see the atomic number is same, right. So, A is same 92. So, the number of neutrons in one is 143 and one has 146. Okay. So, due to this different number of neutrons, we are going to have different mass numbers. So, therefore, uranium has these isotopes. So, isotopes are those which have same atomic number, but variable mass number. Okay. So, for instance, we have 3 isotopes of hydrogen. Hydrogen with mass 1 is called protium. Hydrogen with 2, 1 proton, 1 neutron, it is called deuterium. Hydrogen with 1 proton and 2 neutrons, it is called tritium. Okay. Same thing for carbon, if it is 6 atomic number and 12 mass, it is called carbon 12. Then we have carbon with mass 13 and we also have carbon with mass 14, and they are there with different abundances. So, carbon, if you see carbon, the abundance, the natural abundance of carbon with mass 12 is 98.9%. 13 carbon is 1.1. So, already we have now almost like 100%, and we have very few is this 0.0001% will be 14 carbon. Okay. So, this is the natural abundance. Similarly, if you want to see the natural abundance of protium, deuterium and tritium, you will find protium will be the most abundant, deuterium will be the second most abundant, okay, but it will be very different. So, this will almost be like 99, this will be very maybe less than 1%. Okay. So, this is less than 1%, okay, and then this will be very less than 1%. Okay, their abundance can be very low. Okay, so, that is because these are not very they are not the main the processes that led to the formation of deuterium and tritium, they are not the main processes. It is by somehow they got formed due to some reactions and all that. So, with this I will stop this lecture and we will continue further on isotope geochemistry in the next class. Thank you.